Daniel, and thanks. Right, thanks, Daniel. Thanks to the organizers for inviting me. I'm glad to be talking here and to be participating in the other meetings in the afternoon session. All right, so today I'm going to talk to you about isolating cuts, which is a new tool for solving minimum cut algorithms. Okay, and the talk that I'll give today is based on a couple of papers with Jason Lee, who is now a postdoc at UC Berkeley and Simons Institute. But I've been working in this general area for the last couple of years, and this work has been in collaboration with a lot of different people, some of whom you're going to hear in this workshop as well. So we have, I've worked with Tachapal Sarunarak, Sorachai, Danupananonkai, Ken Quandrad, and my student Roshu Chen. All right, so what's a minimum cut problem? Loosely speaking, here's how we are going to define it. So let's say we are given a graph and we want to find the minimum cardinality cut or the minimum weight cut if the edges of the graph have weights, satisfying some condition. So if it's unconstrained, then it's simply the minimum cut across all the cuts of the graph. But in some cases, it might be constrained, and you might ask for specific properties in which case it's the minimum among the cuts satisfying that property. Okay, and of course, recall that a cut is a set of edges whose removal disconnects the graph into its two sides. So here's an example. Here we are just asking for the unconstrained minimum cut. And in that case, for this particular graph, it's the cut containing that single edge in the middle. Okay, and in this talk, the input graph will always be undirected, although some of the work that we have been doing, not quite related to isolating cuts, but in the general area, is for directed graphs. But as far as this talk is concerned, all the graphs will be undirected. But the graphs can have parallel edges, so it can be a multi-graph, and it can also have non-negative edge weights, so it can be a weighted graph. Okay, so the first one is a weighted graph, the second one is a multi-graph, the third one is a directed graph. We are excluding that from this talk. So what are the minimum cut problems that we are typically interested in? The first and perhaps simplest is what's known as global minimum cut. And this is the problem that's unconstrained. So it's just asking for the min cut across all the minimum weight cut among all the cuts. And this is the example from the previous slide. This is indeed the global minimum cut of the graph, the edge of weight 1. Because every other cut, in fact, has a higher weight. Another problem that's very popular and has been studied for a long time is the ST min cut problem, or sometimes also called the local min cut problem. In this case, we additionally place the constraint that a given pair of vertices S and T must be on different sides of the cut. Okay, and it's well known that an ST min cut has the same value as an ST max flow, and therefore ST min cuts can be found using max flow algorithms. Okay, so here's an example of an ST min cut. So I have chosen two pairs of vertices to demonstrate this. First pair is S and T1, and the cut containing the single edge in the middle is the ST1 minimum cut. In fact, that's also the global minimum cut. But if I chose the pairs S and T2, chose the pair S and T2, then the global minimum cut actually doesn't separate this pair. Both S and T2 are on the same side. So indeed, the ST2 minimum cut is a different cut. In this particular case, it's the cut containing two edges of weight 1 each. Okay, so these are the first two problems that we are interested in. And there's a generalization of these two problems called Steiner minimum cut, in which case we are given a set of vertices, usually called terminals. And the constraint is that you must have at least one vertex from this given set on either side of the min cut. So sometimes we say that the cut must be separating the terminals. Now, if you chose S and T to be your terminals, then it's the same as an ST min cut. If you chose all the vertices as terminals, then this is just a global minimum cut. But in general, you can choose any subset of vertices as terminals. Okay, and again, another example, if we chose ST and T1 and T2 as the three terminals, then the cut, the global min cut, in fact, in this case, separates S and T1. So that's our T1 and T2, and therefore it's also the Steiner minimum cut. But in general, of course, the Steiner min cut may not be the global min cut. And finally, we are often also interested not just in a single min cut, but multiple min cuts. So this comes in two common forms. The first is what's known as single source min cut. So we just fix a vertex S and ask for the minimum cut between S and every other vertex. Or we ask for the minimum cut for all pairs of vertices ST in the graph. Okay, so this sort of gives a very quick landscape of the problem minimum cut problems that are sort of traditionally interesting in terms of algorithms. And we are going to touch upon all these problems in this talk. So any questions about any of the problems before I go along? Okay, so if there are no questions, let me keep going. So what do we know about these minimum cut problems? Here's a very simple fact. So you can, of course, solve the single source min cut problem by simply asking for the minimum cut between every vertex T and this fixed vertex S. So you can just run n-1 iterations of max flow or ST min cut to obtain the single source min cut problem. And the single source min cut problem, like the solution to the single source min cut problem, can be used to solve both global and Steiner min cut. For global min cut, all you do is you just report the smallest of these n-1 ST min cuts. For Steiner min cut, you make sure that one of the terminals is chosen as this fixed source S, and then again you report the smallest among the min cuts that separate us from the other terminals. Okay, so that's a simple fact that we will use as a baseline, that you can solve all these three problems using n-1 max flows. Now, in a really remarkable early result, Debmalya and Hu 60 years ago showed that even the all pairs min cuts problem can be solved using n-1 max flows. Now, this is surprising because the all pairs min cuts is asking for n choose 2 cuts. So that's a quadratic number of cuts, whereas all I'm doing using n-1 max flows is finding just a linear number of cuts. But it turns out, as they showed, that these linear number of cuts are sufficient to answer the ST min cut question for all pairs of all the quadratic number of vertex pairs. Okay, so I'm not going to go into the details of why like how this works, but that's the baseline for all pairs min cuts as well. And using the current fastest max flow algorithms, of course, max flow algorithms have evolved over time, but this gives a running time that's roughly mn if you allow randomization. It's not quite mn if the graph is sparse. It's a little higher for sparse graphs, and a little worse than mn if the if the graph is deterministic. Sorry, if the algorithm is deterministic. So that's our baseline. It's not particularly important to remember what these running times are, but I did want to mention them. So that kind of kind of creates our baseline for all the problems. But for one of these problems, we know a lot better, in particular for the global min cut problem. So here's the baseline for global min cuts. But now if we focus on deterministic algorithms, you can actually do a lot better. You can get all the way down to mn. Okay, so, and this is specifically for global min cut. So this is faster than the best that we know for, like this is faster than what we can do using n-1 runs of max flow. And if we allow randomization, then you can even do better. In fact, you can get a near linear time algorithm, although the algorithm is Monte Carlo, which means that it will occasionally output a wrong answer. of course, the holy grail in this entire area is to get near linear time, O tilde m time for all the problems that I described. So if you could solve all the problems in O tilde m time, that would be kind of a complete picture of the space. Again, just to be clear, so m is the number of edges and the number of vertices, and O tilde will hide log factors. We are not going to be interested in logarithmic or any subpolynomial factors in this stuff. So I'm going to hide them. All right, so that's the state of the art for global min-cut algorithms, far better than we know for the other 4 problems that I described. Okay, so that creates this hierarchy of problems. So global min-cut is sort of at the bottom. So it has a linear time randomized algorithm. Sorry, I'm missing the word randomized there. And a deterministic algorithm that's mn time. ST min-cut is sort of the next tier, where we have algorithms that don't quite get all the way down to linear time, but are relatively close. And then the third tier are all the 3 other problems. All of them essentially at this point still take n-1 max flows. So there is, for example, for the single source min-cut problem, there is no non-trivial algorithm that goes beyond just running n-1 iterations of ST max flow. Okay, so that was the state of the art. Now let's look a little closer at the bottom boxes, the 2 boxes at the bottom, ST min-cut and global min-cut. These are also, in some sense, the most well-studied among these 5 problems. Now there is this strange thing going on here, where the global min-cut algorithm is faster if you allow randomization, but is slower if you restricted yourself to deterministic algorithms. So one question that arises is whether we can actually obtain global min-cuts deterministically in about the same time that we can do randomize. So that this, at least one effect of that would be establishing this clear hierarchy that global min-cuts are indeed easier than ST min-cuts. Okay. So let's ask that question. So can we obtain a deterministic global min-cut algorithm that runs as fast as a deterministic ST min-cut algorithm? Okay, so this question, of course, in various forms of this question had been asked since the 90s, but there wasn't a lot of progress till about 6 years back. So in Stock 2015, in a paper that in fact recently won the Fulkerson Prize, Kawarabayashi and Thorup gave a deterministic near linear time algorithm for global min-cuts. But one caveat was that the algorithm only works for simple graphs. And this is somewhat fundamental in the sense that it's not just that the algorithm is slower if you have parallel edges or weights on the edges. The algorithm actually can produce a wrong answer. Okay, so the algorithm is correct only for simple graphs, but on simple graphs, it does run in time that's near linear and therefore resolves the question that we are after. And in fact, the initial algorithm had a pretty large logarithmic factor, which was improved a couple of years later by Hensinger, Rao, and Wang. So our first result is that there is, in fact, a deterministic algorithm for the global min-cut problem, and this is in the general case of weighted graphs that uses polylog and max flow calls. So up to this polylog factor, this answers the question on top. So this gives you a deterministic global min-cut algorithm that's as fast as a deterministic ST min-cut algorithm. And the use of the ST min-cut algorithm in our case is completely black box. So you can feed in any max flow algorithm that you wish. All right, and in fact, Jason Lee went on to improve this result in a later paper that came out this year, where he actually gets a deterministic algorithm for the global min-cut problem that runs in near linear time. Okay, so that completely solves the problem and essentially gives a deterministic algorithm that has the same running time as the best randomized algorithms. Okay, but we're going to focus on the first result because it gives us this new technique called isolating cuts that we are going to talk about more. So what is the idea of this result? So the main new idea is this notion of isolating cuts that I'll describe. And then if once you have isolating cuts, that pretty much immediately gives you a very simple randomized minimum cut algorithm. Okay, so I'll describe the isolating cuts principle, and then I'll talk about what this randomized min cut algorithm is. Now our eventual deterministic algorithm de-randomizes this entire process using expanded decompositions, but this is something I'm not going to talk about today. Okay, so if you are interested, I welcome you to read the paper, but this is, and there are some interesting ideas in the last step, but we are going to focus on the first two. Okay, so in order to understand isolating cuts, let's recall this very naive global min cut algorithm that uses n-1 max flows. So what does it do? It fixes a vertex S and returns the smallest ST min cut over all n-1 vertices T that are different from S. Now, one way of viewing this algorithm that it essentially is trying to find a pair of vertices S and T that are on different sides of the global min cut. It doesn't have a better way to do this than to fix S and then iterate over all other possible vertices T. But if it were given such a pair of vertices S and T, then all it would have needed to do is just run max flow once and it would be done. Okay, so at the heart of what we do is the question that we started off by asking, which is basically, can we find such a pair of vertices S and T more efficiently than this naive iterative algorithm is doing? Now, this question is rather simple, at least conceptually, if the min cut is balanced, i.e. if you have a lot of vertices on both sides. So for instance, if you have, let's say, omega n vertices on both sides of your min cut, then all you need to do to find a good vertex pair, a vertex pair that straddles the min cut, is to just sample. Okay, now, of course, our eventual goal was to obtain a deterministic algorithm, and therefore every time I say that we can sample, there is something going on in the background that will de-randomize this. I'm going to ignore the de-randomization just to focus on the conceptual idea. So as far as the conceptual idea is concerned, if the min cut is balanced, we can simply sample a bunch of times, let's say log n times, and one of those pairs with high probability will be straddling the min cut. So if we just sample log n pairs, find their min cuts, report the smallest one, that's going to be a good algorithm. Now, suppose the smaller side of your min cut has k vertices, and think of k being small. So k is little of n. So then, of course, if you simply sample a bunch of pairs of vertices, log n pairs, then we are not going to get a pair that straddles the min cut. Let's do something else in that case. So let's imagine sampling every vertex independently with probability about 1 over k. Okay, so what I'm doing here is that from the smaller side of the min cut, the side that contains k vertices, I'm trying to make sure that my sampling chooses in expectation exactly one vertex. Okay, so now how do you know k? This is not very difficult. You can basically guess k. You can do you can run this sampling procedure for all possible values of k. Okay, and just up to you can approximate k up to a factor of 2 by using doubling ranges, and then in log n iterations you would hit all possible values of k up to a factor of 2. Everything that I say about sampling will not be affected by this error in accuracy of the sampling probability. Okay, so again, conceptually think of your min cut having k vertices on the smaller side, and you are sampling every vertex in the graph independently with probability 1 over k. This gives this very simple property that comes from elementary probabilities. So your sample will have exactly one vertex on the smaller side with constant probability. Okay, and if you repeated the process log n times, then with high probability, there will be a sample that has exactly one vertex on the smaller side. And it's important for what we say later, that it exactly has one vertex. So more than one vertices is not good. Of course, having 0 vertex is also not good. So you want exactly one vertex on the smaller side. Okay, but the problem, of course, is that the larger side will have many vertices. So of course, if I had exactly one vertex on the smaller side in the sample and exactly one vertex on the larger side as well, then I got my pair that I was looking for, the pair that I can now run MaxFlow on. But in general, if k is, particularly if k is small, I'll sample a lot of vertices on the larger side. And although I will have this property that exactly one vertex lies on the small side, I wouldn't know which one, right? So naively, I won't be able to do anything once I sample. The extreme case of this would be if your min cut indeed is a degree cut, in which case you're basically sampling all the vertices to ensure the property in the third bullet, and the sample has no additional information, it's just all the vertices. Okay. Okay, and here's an example. So let's say the min cut was this SV minus S cut, and we were sampling vertices. A sample that satisfies the criterion that I was talking about of having exactly one vertex on one side, on the smaller side, is what is shown here. If you sampled vertices A, B, C, and D, the vertices circled in green, then indeed you have just one vertex D on one side of the min cut. Okay, so this is the kind of sample that's going to be useful for us. And as I described on the previous slide, obtaining such a sample is not difficult. So we have essentially now reduced our global min cut problem to the following one. So we are given a graph and a subset of vertices. So this subset is the sampled vertices. And we need to find the minimum cut that separate each vertex T from the rest of the vertices, right? So if I'm able to find the minimum cut for each vertex, each sampled vertex from the rest of the sampled vertices, then reporting the minimum among all of those cuts will give me the global min cut, because of this property that one of these cuts, one of the cuts that separates a single vertex from the rest of the vertices in my sample, must be the global min cut itself. Okay, so my task now is to find these cuts that separate one vertex out of the T vertices from the rest of the vertices in the sample. Okay, and this is what we call isolating cuts. Okay, because they're isolating a single vertex from the rest of the vertices in this selection of vertices. Any questions about what isolating cuts are? I'm going to tell you how to solve it, but I want to answer any questions about the definition first.
All clear on our end.
All right, thanks. Thanks, Daniel. All right, so let's keep going. Okay, we call this the isolating cuts problem. So naively, a simple algorithm would be to simply use T-1 max flows, right? So what we can do is for every, or actually this needs T max flows, it shouldn't be T-1. So basically I fix every vertex, I collapse all the other vertices into a single super vertex, call max flow between this pair, and I can repeat this, iterate over all the vertices in my sample. So using T max flow calls, not T-1, I'm sorry for the error. Using T max flow calls, you can find all the isolating cuts and then simply report the minimum amount. So that's the naive algorithm. But this is rather useless. Think of the example that I described earlier of your min cut being a degree cut, in which case this subset of vertices T is in fact all the vertices. So this technique of running max flows individually for all the vertices in T could take as many as n max flows. So we are back at the basic algorithm, like the baseline algorithm that we started with. Okay, so our main lemma is that we can solve the isolating cuts problem in log T max flow calls. So again, contrast with T max flow calls, which is the naive algorithm, we are going to exponentially improve this. So we are going to solve this problem using log T calls. So I'm going to show you how to prove this lemma, the algorithm that proves this. But before I do that, let's look at a simple randomized algorithm that this lemma immediately implies. And this is something I've already sketched to some extent, but let me put this down on a slide and go over it one more time. So recall that I'm calling my minimum cut, the global min cut, S and B minus S, the two sides of the cut. We guess the value of S, let's say the smaller side. More precisely, we choose I such that S is between 2 to the I and 2 to the I plus 1. And to do this, we iterate over all the possible values of I. Okay, then we sample vertices independently at random with probability 1 over 2 to the I. This forms log n independent samples, T1, T2, etc., till T log n at these different levels of sampling. And then we claim that with high probability, at least one sample Tj has exactly one vertex on the smaller side of the global min cut. Of course, in order for this statement to hold it with high probability at each level of sampling, we also need to sample log n times. So we have this matrix of samples, log n different levels of sampling. Each level you have log n different samples. Of this log squared n independent samples, we can claim now that with high probability that at least one sample will have exactly one vertex on the smaller side of the global min cut. Okay, and then we simply use isolating cuts. We use isolating cuts on all these log squared n samples and simply report the smallest cut that these isolating cut calls reveal to us. Now, of course, one thing to note is that even if the sample satisfies no properties, the cut that it gives back, the cut that isolating cuts returns, is some cut in the graph. So there's no scope for me to output a spurious cut. The only thing I need to establish is that I do see the minimum cut in one of these runs, and that's what we are establishing. Okay, it isn't going to be the case that in a run that doesn't have the properties of the sample that we desire, we are going to get some cut that's smaller than the min cut. That's not possible. We are still going to get a cut. And by definition, the min cut is the smallest. Okay, so all I need to establish is that I do see the min cut in one of these runs. And that's exactly what we argued earlier. Okay, so that's the simple randomized algorithm. And as I said, this can be de-randomized. But let's switch to trying to show the isolating cuts lemma. Okay, so again, remember what was the lemma saying? I give you a graph, I give you a subset of vertices. I want to make sure that I find the minimum isolating cut in log T runs of a max flow algorithm.
Sorry, quick question on the simple algorithm.
Yeah.
Just want to clarify. So that would give a runtime proportional to the runtime of solving on the order of a polylog number of max flows.
That's exactly right.
But not actually solve the problem with polylog max flows.
What do you mean by proportional to it?
It's going to call max flow many times, but on problems of smaller size. Not
that's right. Well, I mean, so far it's still running just log squared max flows. Eventually, we are like my isolating cuts lemma at the moment is a black box.
Wait, when we sample at a high rate, we don't need to run it because we don't know which one will actually. Oh, I see. Okay, I see. Thanks.
Okay, so but you are right. Once I open up the isolating cuts black box, you will see that what you are saying is exactly right. It won't be precisely log n calls, but it will be a lot more calls on smaller graphs that add up to log n max flows. Okay, but so far it's just simply log squared and isolating cuts. Any other questions? Okay. So here's how we prove isolating cuts. So we start off by taking these T vertices, the vertices that I selected in my sample, and simply labeling them using log T bits. Okay, so I just label them using in binary. And now I look at every bit position. So every bit position essentially splits the vertices into two equal halves. And for a second, let's imagine that T is a power of 2. It doesn't really matter. But every bit position splits the set of vertices into two equal halves. So what we do is we partition the vertices into these two sets. So let's say for bit position k, the vertices that were labeled 0 in that position, let's call those vertices xk. The vertices that were labeled 1 in that position, let's call those vertices yk. And then all we do is find an xk to yk min cut using max flow. So basically we take all the vertices that had a 0 in the kth position, contract them into a single super vertex, take all the vertices that had a 1 in their kth bit position, contract them into another super vertex, and then run max flows or st min cut between those two super vertices. Okay, so an example is shown here. We have 4 vertices A, B, C, and D that were selected in T. So we are just using 2 bits, and you can see that the zeros. So if I took the first bit position, then the 2 zeros form this set xk on top. Okay, if I took the second bit position, then the 2 zeros, the red zeros form xk to the left. So x1 is the blue set, x2 is the red set, and the complements are y1 and y2 respectively. Okay, and we are just finding the minimum cut between xk and yk in for each bit position k. Okay, so now what we do is we take all these log t minimum cuts. So each of these max flow calls will return an st min cut for me. So I take all these log t cuts and I simply remove all these edges from my graph. Okay, just take all the edges out. Now the claim is that every pair of vertices in T is separated by at least one of these cuts because no pair of vertices had the same bit encoding. So in particular, every pair had one bit position where one vertex was labeled 0, the other vertex was labeled 1. And that bit position, for that bit position, we found some min cut that separates all the vertices labeled 0 from all the vertices labeled 1. And therefore, every pair of vertices must have been separated by one of these log t cuts. Okay, so if I remove all these edges, the edges in all these log t cuts, then that splits my graph up into t parts, into t pieces, where each piece contains exactly one selected vertex from T. Okay, so that's the picture I want you to keep in mind. You take cut these edges out, and suddenly the graph splits into these connected components, or maybe even disconnected components, but each of those parts contains a single minimum cut. Sorry, a single selected vertex in T. Okay, so here are the 4 parts that we get in this particular graph when we remove the 2 cuts corresponding to the minimum cuts between xk and yk. Okay, so the next thing we do is to sort of run a separate algorithm for each of these parts Si. So let me call these parts S0, S1, S2, and S3 that respectively contain T0, T1, T2, and T3. And for each of these parts, we run a separate algorithm. So what does that algorithm do? It keeps the ith algorithm, keeps Si uncontracted, so maintains it as is, but contracts everything else outside. So for example, if I'm running this it for S3, I will keep DEF, that part of the graph, uncontracted, but contract S0, S1, and S2, so A, B, and C into a single vertex. Okay, so we call that super vertex ZI. So you get the uncontracted part, which is Si, and everything else, everything in the external world gets contracted into a single vertex called ZI. Okay, and we run a minimum cut now, another max flow call, an st min cut between the Ti and Zi. So the contracted vertex Zi that contains everything outside Si, and the special terminal that's sitting inside Si. Remember, there's exactly one terminal inside Si that's called Ti. So if I'm running this for S3, then T3 will be one of the end, one terminal for my st min cut call. The other terminal will be S0, S1, and S2 collapsed into a single vertex called Z3. All right, so that's the algorithm that we run, and we run it for every vertex in T separately. Okay, so again, here's a depiction. All these three vertices will go into Z3, get contracted into a single vertex, and then we just run a T3 Z3 min cut. Okay, so the main claim is that this, if I run such a Ti Zi min cut in this graph GI, where I've contracted everything outside Si, then this is in fact a minimum cut in the overall graph that separates this vertex Ti from the rest of the terminals. So if I go back here, you can see that if I got a cut after contracting Z3, if I got a minimum cut between T3 and Z3, that certainly separates T3 from T0, T1, and T2. So that is a valid isolating cut. But is it the minimum one? This claim says it is. So it says that the fact that I'm contracting all these vertices outside Si does not change the identity of the minimum cut that separates Ti from the rest of the terminals in the graph. Okay, and this is a property I'm not going to prove. This is it's a fairly simple proof, but it needs this additional tool called uncrossing, which is a classical tool in minimum cuts. But in the interest of time, I'll skip the proof of this claim. But if you believe me on this claim, then that gives you immediately establishes the correctness of the isolating cut algorithm. Because if indeed the Ti-Zi min cuts are the minimum cut separating Ti from every other vertex, then simply reporting these cuts will give me the isolating cut for every terminal vertex Ti, and the minimum among them will be the minimum isolating cut of the graph. Okay. So then the question becomes, how many max flow calls am I making in this algorithm? So there are two phases to the algorithm. The first phase use the bit encoding and then use the positions of the log T different positions to run max flows. Okay, so in the first phase, of course, I only have log T max flow calls. So this is to produce this partition into the sets of vertices that I called SIs. Okay, so the first phase takes log T max flow calls. But the second phase, apparently it seems like we're actually using T max flow calls, because for each of these segments that we got out of the first phase, each segment Si, I'm actually running a max flow, a separate max flow between Ti and Zi, between this terminal Ti that's sitting inside Si and this contracted vertex Zi that contains everything outside Si. Okay, so we certainly have T max flow calls in the second round. But the key observation is that cumulatively, these T max flow calls aren't operating on too many edges. So let's look at the edges that any such max flow call is operating on. So here's a sort of schematic diagram. So you have Si, which is uncontracted, which is the blue part that contains this terminal Ti. And you have Zi, which is contracted and contains everything that's outside Si. Okay, so all of Zi is contracted. Edges inside Zi don't show up on this max flow. So what are the edges that do show up? There are two categories of such edges. The first are edges that are internal to Si. Now, of course, these edges are unique to this particular max flow call, right? An edge that's internal to Si is not going to be internal to any other Sj. Therefore, the edges inside Si are exclusive to only one of these T max flow calls. And then there are these edges that interface between Si and Zi. But these edges, I claim, only show up in at most two max flow calls, because if you have an edge that goes from a vertex in Si to a vertex in Sj, then it shows up in the max flow call for Si and it shows up in the max flow call for Sj, but it does not show up in any other max flow call, because Si and Sj will get contracted into Z in all the other calls. Okay, so every edge either shows up precisely in one of these max flow calls or in two of them, depending on whether it's internal to an Si or it interfaces between two different Sis. between Si and Sj. Okay, so that says that the total number of edges that I'm working with in these max flow calls is no more than 12. And therefore, effectively, all these T max flow calls run in time that's proportional to a single max flow call or a constant number of max flow calls. Any questions about this? That's the end of isolating, like of the proof of isolating cuts. And then we'll talk about some more applications.
So Debmalya, yeah, the number of
Yeah.
vertices can be n, close to n in all the, or most of the.
No, so there are two types of vertices. So there are vertices that are in Si. So this is a partition. Si is a partition of the vertices. So vertices internal to Si only show up in a single call. And then every max flow call has this additional vertex called Zi, which is just a contracted vertex for everything outside Si. But that's one vertex per call. So that's no more than n either.
Okay,
Does that make sense?
Yes, I think he's satisfied.
Okay, thank you. All right. So let's, so that establishes the isolating cuts lemma. Let's see how that makes life easier for us. So firstly, here's an observation. So the isolating cuts framework, although we sort of described it in the context of global min cuts, it didn't really use anything specific about global min cuts. So what was the main idea? So the idea was that if I want to find a minimum cut subject to some conditions, I need to sample a set of vertices such that exactly one vertex appears on the smaller side of whatever minimum cut I'm trying to find. And once I have that property, I can use isolating cuts, right? So in the particular case of global min cuts, I didn't have any constraint on what set of cuts I'm trying to find the min cut over. But even if I do have a constraint, as long as I can satisfy the second criterion that I manage to sample exactly one vertex on the smaller side of the cut, I can still use isolating cuts. And indeed, let's think of the Steiner min cut problem. So here we want to find the smallest cut with at least one terminal on each side. Okay, so I am given a graph, I'm given some subset of terminals. I want to find the smallest cut with at least one terminal on either side of the cut. So all I need to do if I want to use isolating cuts is simply sample from the terminals rather than all the vertices. So if I sample from all the terminals instead of all vertices, then at the right rate of sampling, I'll again ensure that I have exactly one terminal on the side containing fewer terminals. Okay, and if once I have that property, if I use isolating cuts, it will reveal my Steiner min cut, right? Because again, I have exactly one terminal on the smaller side. I have multiple terminals on the larger side. Isolating cuts figures out what's the smallest way of separating the one vertex from the rest of the vertices in the sample set. So if pretty much immediately, it gives you an algorithm for Steiner min cuts. And this is the statement that you get. There's a deterministic algorithm for this problem that uses log and max flow calls. And as I said earlier, so when I say that it uses log and max flow calls, I'm taking this liberty of calling that last step a single max flow call, right? Although it's really a lot of max flow calls that add up to the cost of just one call. But for Steiner min cuts, this wasn't known even if you allowed randomization. So for global min cuts, if you allowed randomization, fast algorithms were already known. Steiner min cuts, no algorithm was known even if you allowed randomization. So that simplifies this picture. So in two ways. The first is in global min cuts, where we can now replace these like deterministic and randomized algorithms by a single runtime. Of course, this eventual runtime of M doesn't come from the isolating cuts directly. For this, you need this additional work, that follow-up work of Lee. But at least even with just basic isolating cuts, you would ensure that your running time for global min cut deterministically is no higher than that of ST min cuts. up to logarithmic terms. And then it also solves Steiner min-cut. So remember, Steiner min-cut was in the box on top. So it needed n-1 max flow calls, even if you allowed randomization. From there, we have now moved it to the box in the middle, because now it only requires polylog max flow calls. Okay, so we now have this sort of, the hierarchy has changed. Global min-cut still remains at the bottom. Then we have ST min-cut and Steiner min-cut, which are the same up to polylog terms. And then we have all pairs min-cuts and single source min-cuts. Again, they are the same up to polylog terms.
Debmalya,
Yeah.
just for the global order M like min-cut algorithm, I guess there has to be some intelligence to get the dependence on N to disappear.
That's right. So in particular, you are not allowed to make max flow calls, because we certainly don't know how to solve max flow in near linear time.
Okay, just checking.
Yeah, yes, absolutely. And this, in fact, doesn't use isolating cuts at all. So it's basically at a high level is a de-randomization of the previous randomized algorithm.
Ah, I see. Okay, thanks.
Okay. So this is our new picture. So let's look at this a little more carefully. So here's how min-cut problems are organized in terms of what generalizes what problem, right? Like which problems generalize other problems. All pairs min-cuts, of course, generalizes everything that we have talked about. Single source min-cuts is generalized by all pairs min-cuts, but actually generalizes everything else in our picture as well, right? Because if I give you single source min-cuts, as I described earlier, you can find Steiner min-cut, you can find ST min-cuts, you can find global min-cuts, etc. Steiner min-cuts also generalize both ST min-cut and global min-cut. In fact, the problem is defined in a way specifically to generalize these two problems. And then we don't really know, there's no real generalization between ST min-cuts and global min-cuts. These are kind of independent problems. Now, what we have done, one way of thinking of that is that we have ensured that the two circles of representing Steiner min-cuts and ST min-cuts, they now get connected by a double-sided arrow, which means that these problems are equivalent. And when I say equivalent, they're equivalent up to polylog factors. Okay. Now, there's another equivalence that we can show. So this sort of was independently discovered by Abud, Krautgramer, and Trebelsi, and also in a paper that I had with Jason Lee. Our results are slightly different in what gadget it requires, but that's a minor point. The basic idea is that these results can show that single source min-cuts and all pairs min-cuts are equivalent, again, up to polylog terms. So if you give me a single source min-cut algorithm, I can solve all pairs min-cuts as well. Okay, so we have these two equivalences. So because of these two equivalences, we kind of get these three boxes. We have all pairs min-cuts, single source min-cuts as the top box, Steiner and ST min-cuts in the middle box, global min-cut at the bottom box. And the two gaps that we still have are kind of the biggest questions in the area. The gap at the bottom is asking, is there a near linear time max flow algorithm? Right, so can we collapse ST min-cuts into global min-cuts in terms of running time? That would mean that we have to design a near linear time max flow algorithm. The gap at the top is asking, can we solve single source min-cuts faster than the naive one that just runs n-1 ST min-cuts? Okay, and in fact, this has been a long-standing question. So let's look a little deeper into this question. So Gomory and Hu gave this really beautiful algorithm in 1961 that finds all pairs min-cuts using just n-1 max flow calls. And the really surprising thing is that 60 years later, this remains the state of the art. So we still don't have a better algorithm, better general purpose algorithm for this problem. Now, this is not due to lack of trying. So faster algorithms are known for all pairs min-cuts in pretty much every meaningful subclass that you can think of. planar graphs, surface embeddable graphs, bounded tree width graphs, simple graphs, unweighted graphs, and I'm sure I'm missing a few. So a lot of special cases have resulted in algorithms that run faster, but the general problem still remains open 60 years later. So on general graphs, we still don't have a faster algorithm. And in fact, as we saw on the previous slide, this is true even if we replace all pairs min cuts by just single source min cuts. The difference is that for all pairs min cuts, this n-1 max flow algorithm is a non-trivial algorithm. It's not immediate. Whereas for single source min cuts, this is completely trivial, right? I just fix a source and find max flow to every other vertex. And it's a fascinating question. Is this algorithm really the best one, right? And if we are able to show that there is a better algorithm for this problem, then we make progress on this 60-year-old question that we haven't made progress on, in spite of much effort in various special cases. Okay, so that's the arrow between the top two boxes that we still need to solve. But let's take a slight digression and think of approximation algorithms. So suppose we ask exactly the same question, but now allow a 1 plus epsilon approximation. Now, the first thing to note, of course, is that global min cuts don't really require this, because we can solve the problem exactly in near linear time, so we don't care about approximations. But the other problems might. And in fact, these two questions now translate to asking if there's a near linear time 1 plus epsilon approximate ST min cut algorithm, and is there a 1 plus epsilon approximate all pairs min cuts algorithm that runs ST min cut fewer than n-1 times. And here I am, so you can ask for a gadget that runs exact ST min cuts, or you can ask for a gadget that runs approximate ST min cuts. And this difference is important, and we'll talk a little bit about this difference in a couple of minutes. Okay, but let's ask for the easier one first. Can we solve it using exact min cut calls, but fewer than n-1? So first, let's think of the box in the bottom, solving approximate max flows in near linear time. Of course, we now know that this can be done. So in a series of beautiful works, Sherman, then Kellner, Lee, Orecchia, and Sidford, and eventually Richard Peng, gave algorithms that solve approximate max flow 1 plus epsilon approximate ST min cut in near linear time. And these papers differ in what near linear precisely means. It could either be logarithmic factors or it could be sub-polynomial terms, but let's not, that's a sort of lower order point. And in recent work using the isolating cuts framework, Jason, Lee, and I showed that indeed you can also solve the question on top. So in particular, we want to solve approximate all pairs min cuts faster than n-1 max flows. So using isolating cuts, we give an algorithm to find 1 plus epsilon approximate ST min cuts for all pairs of vertices using just polylog n exact max flow calls. Okay, so and using the best max flow algorithms that yields the same running time as max flow, which is like m plus n to the 3 halves up to polylog terms. But note that it's not getting linear time algorithms, right? Because what we are using as a gadget is an exact max flow algorithm. Although what we are eventually ending up with are approximate all pairs min cuts. So this is kind of a strange thing going on, right? And there's a reason for this. The reason is that if you remember, one thing that I didn't show you is a proof in isolating cuts that uses uncrossing. Right, so the reason that isolating cuts, the entire thing works, is because of this phenomenon called uncrossing that I didn't go into. It turns out that uncrossing fails the moment you use approximate min cuts, right? And this is a well-known issue with approximate min cuts. So the isolating cuts gadget cannot work with approximate calls, even if it's being used to solve something approximate. So that's one deficiency of this gadget, and therefore what we get is an exact max flow based algorithm for approximate all pairs min cuts. Okay, now isolating cuts are useful for a broad range of algorithms. I didn't get a chance to talk about all of the ways that isolating cuts have been used recently. But we have been using this for various things. It's useful for finding faster algorithms for vertex connectivity, faster all pairs min cuts in simple graphs, for faster algorithms for connectivity augmentation, splitting off, expanded decomposition, etc. So really, in a lot of problems, we hadn't had progress for many years, maybe somewhere in the ballpark of 20 to 30 years. And it seems isolating cuts at least contributed something conceptually to the area so that we could now make progress on many of these questions. Of course, these individual results require other ingredients. It's not just a straightforward use of isolating cuts, but one of the main ingredients that drives these algorithms is indeed isolating cuts. Now let's return to this question of exact versus approximate. So if we were able to replace exact by approximate, what would happen? Well, this entire picture would basically collapse into near linear time algorithms for all the problems, right? So if you got an approximate ST min cut algorithm, firstly, we have a near linear time approximate ST min cut. Now, if I can use that log n times to solve approximate all pairs min cuts, then the problem that was sitting at the top of the hierarchy that generalized everything that we have been interested in this talk is now being solved by approximately by just log n or polylog n invocations of a near linear time approximate mass flow algorithm. Okay, so all the problems we would approximate versions of all the problems would then be solved in near linear time. Right? So that's kind of the holy grail in this research, getting to near linear time algorithms, and at least up to allowing these approximations if we would have solved the problem. The bigger open problem, of course, here is what can we do with like all pairs min cuts? This is the 60-year-old question that I talked about earlier. So is there a single source min cuts or an all pairs min cuts algorithm that's faster than the one that runs ST min cuts n-1 times? And I am hopeful that I can come back to you and talk to some of you in a little time, in a few months maybe, and talk about, say something intelligent about both of these questions. Thank you very much.